Well, next Thursday being Christmas, of course, that's normally Linda Moulton Howe's slot for us. So we moved her up a week, which means today. She's here with a series of some incredible stories, including, of course, what's happening to the Earth's magnetic pole. Is it shifting? Are things changing? And what does it mean to us if there's that shift? She'll be talking about that in a moment on Coast to Coast AM. Well, the award-winning producer and investigative reporter is back with us, Linda Moulton Howe. Linda, are you ready for Christmas?
Well, I'm getting there, and happy Christmas and New Year's to you.
You too. I'm looking forward to a good 2015. I hope you are too.
Well, I think that if 2014 is any sample of what's coming, we're going to be in a year that is just going to be intensely changing with all kinds of phenomena. And one of those that I am especially interested in is what is happening to the inside of our Earth that is affecting the surface and perhaps the ionosphere, and could it all be related to the potential for a actual pole flip reversal of our north and south magnetic poles?
Almost like the movie The Core. Tell me what you've done on this one.
Well, we have to go back 786,000 years ago. That's when iron atoms in the Earth's liquid outer core, that's where the magma is, began switching their orientation, and they were opposing the existing Earth's magnetic field. Now, what causes iron atoms to act like tiny magnets that revolt against the planetary magnetic field is not understood. But when it happens in increasing numbers, patches of these reverse-aligned iron atoms keep growing until they dominate the rest of the Earth's liquid outer core, and then the planet's magnetic field flips. That means what was the north magnetic pole becomes the south magnetic pole, and what was the south becomes the north. And according to ancient sedimentary rock, volcanic ash, seafloor research, there have been 184 polarity changes in the last 83 million years. Recent ground research indicates that in the century before that last pole flip, the Earth's magnetic field weakened and strengthened several times before the flip. Now, recently, the November 2014 issue of Geophysical Journal International had this headline, quote, "Earth's magnetic field could flip within a human lifetime," close quote. The new study focused on a layer of volcanic ash in the ancient lake sediments now exposed in mountains east of Rome, Italy. The layers indicate that the last magnetic pole reversal, quote, actually happened very quickly in less than 100 years, close quote. Now, in addition to the groundwork in Italy, high above the Earth in the first 6 months of 2014, the European Space Agency's swarm satellites measured a dramatic decline in the magnetic field over North and South America, and it's strengthening. The magnetic field is over the southern Indian Ocean. The data indicates that the Earth's magnetic field is decreasing 10 times faster than normal. And over the last 20 million years, the poles have reversed on average about every 200,000 to 300,000 years. And since that last pole reversal, 786,000 years ago, Earth is now long overdue for a pole change. Could this planet right now be in the early stages of such a pole reversal? And what will actually happen when north-pointing compasses make a 180-degree turn toward Antarctica? What will happen to Earth life such as birds and marine animals that depend upon magnetic fields for guidance? And what happens to humans? I took these questions to one of the lead investigators in the Italian ash research, Dr. Paul Rennie, Ph.D., Professor of Earth and Planetary Science and Director of the Berkeley Geochronology Center at UC Berkeley in California. Here now is Professor Rennie.
The Earth's magnetic field overall is weakening in intensity, and it's also changing orientation at what seems to be an accelerating pace.
So what has changed that we now are seeing headlines that the magnetic poles of this Earth could change in this century?
Okay, so what has changed is a group of my colleagues based in several different institutions in Rome have been measuring the magnetic field of lake sediments in central Italy. And another one of my colleagues who's in Paris, he's French, has been working with this group to date volcanic ashes that blew into the lake when it was actually a lake. Now it's all dried up and you can go out and sample the outcrops. So what they have done is a very, very meticulous job of analyzing a sample every centimeter over a distance of several tens of meters, and they can track what the magnetic field is doing in great detail. And what they see is as you approach this reversal from below, you see a couple of little flickers. You see the field, it was reversed, and then it sort of becomes normal just very briefly, then it goes back again, and then it goes back, and then finally it just snaps into the normal configuration.
So there's oscillation in the field strength before the pole flip.
Yeah. So what you see is changes in the intensity of the field and the direction of the field. And what we have been able to do is by dating volcanic ash above, that happened after the flip, and one that happened before the flip, we can estimate, first of all, how fast the sediments were deposited, so we know how much time, say, what 1 centimeter corresponds to, and we know that rate is consistent with what we get doing the same thing above and below this whole section. So that's what enables us to say the last snap between reversed and normal polarity happened between two samples that are only 2 centimeters apart. That has to correspond to 100 years or less. So we know that final flip happened over less than 100 years.
What is going on in our planet that causes the magnetic poles to flip in the first place?
That is the big question. And many people before actually have concluded that Earth's magnetic field originates in the core of the Earth, in the liquid part of the core, which is the outer part. So that's about 2,900 kilometers deep within the Earth. About
1,800 miles?
Yeah. So from that portion of the Earth where there's a very iron-rich, dense liquid, it's very hot, and it's convecting. And there are electrical charges in that molten iron, and moving electrical fields generate magnetic fields. And so that's where the Earth's magnetic field is generated. It's called a dynamo. And there's a feedback between the magnetic field that's produced, which generates the flow of the ionized iron atoms, which in turn keeps generating magnetic fields. So this property of a dynamo is that it's, to some extent, self-perpetuating. That's the understanding of what's happening where the Earth's magnetic field comes from. But some of the details remain completely unknown. For example, why the poles flip, why the field reverses episodically, is not well known. And what triggers it in the first place? Over the years, people have tried to determine whether there's any periodicity to this. And it seems that there's not, at least not that anybody's ever figured out. So it seems to happen at irregular intervals. Exactly what triggers it, we don't know. And even the process of how it happens, we don't know. But we know that it does happen, and we know where it originates.
With this swarm research and yours, it sounds to me like that one thing that has been established is that there are going to be a pendulum or swinging of weakening and strengthening magnetic fields before the actual magnetic poles flip, and that during that period of time, that what you all are focusing on is that it could be as short as 100 years from now.
Yes, that's right. Now, one of the caveats to all this, though, is that we don't really know whether this recursory flickering business, whether that's always the case, whether every reversal has this sort of behavior beforehand, in which case we could say, well, maybe we're just looking at the beginning flickering and the actual full reversal might be still a couple thousand years in the future. We don't know whether that's a generalization that we can draw or whether that's just what happened the last time and the next one may be completely different. So that's why we can't really predict when it's going to happen based on what we see in the record.
If we are in a century in which the magnetic poles of the Earth are actually going to flip again since 786,000 years ago, and if it is true from the investigation in the ash in Italy that there are these weakening, strengthening pendulum swings of the magnetic field before the flip, then aren't we in a very uncertain time in which animals such as birds and marine animals that are so dependent upon magnetic fields could be faced with challenges of survival while all of this pendulum swinging of magnetic fields took place?
I would say that it's possible, yes. Yes. We don't know that that's going to happen imminently, but we know that it has happened that way and may happen again.
And what would happen to Homo sapiens sapien humans?
Well, I'm not really qualified to answer that, but I know that there has been some speculation about that. In fact, a very eminent geomagnetist in Paris named Jean-Pierre Vallée published a paper a couple of years ago postulating that the extinction of the Neanderthals was caused by a brief magnetic event that was like a reversal, but it didn't last. It was one of these really short events I mentioned earlier. Reasoning there was that when the Earth's magnetic field changes abruptly and the intensity decreases, the strength decreases, you can get major bursts of ultraviolet radiation, which the Neanderthals were not very well adapted to.
If the magnetic field strength goes down to zero or near zero, during that period of time, the entire planet is vulnerable to solar radiation, which can kill.
Yeah, and not just solar radiation, but so-called cosmic radiation, which actually comes from beyond our solar system. And a lot of these things are high-energy charged particles, protons mainly, and they're deflected by the magnetic field. In the absence of a magnetic field, the flux of these things is going to go up considerably. We know that during periods of magnetic reversals, we can see, in fact, that there is an increase in cosmic radiation. So to the extent that that's going to have a negative impact on life, then yes, that's definitely something to be concerned about.
Have you and other geophysicists been brought into the Department of Defense to talk about what might happen if this pendulum goes up and down in magnetic field strengths and affects Earth life?
No, but somebody ought to.
What would you advise?
Well, I would advise that people who know more about the biological effects than I do be consulted, or of the technological consequences. What does this kind of thing mean for the power grid, for satellite communications, for transportation? All of these things are potentially going to be affected, and there are people who do have relevant knowledge who should be consulted. And frankly, I'd be surprised if the DoD wasn't actually tracking this and talking to these people, but I'm sure it would be not well publicized until some conclusions had been drawn, because the government doesn't want to terrify people prematurely.
What would be causing this accelerated or very rapid weakening of the magnetic field over the Western Hemisphere and the Indian Ocean?
Well, what's happening right now with the so-called dipole low over North America is an instantaneous thing, and it's moving relatively rapidly. The weak area is moving, And so I don't think we can say anything about what that portends for the final, what's ultimately going to happen. That weak spot is moving.
Is your hypothesis that the weakening, strengthening, wherever it is related directly to the core, that there is a change in the Earth's core now?
There must be something, yeah. I mean, there must be something in the outer core that's causing it, sure, yeah. The thing is, we don't completely understand what the thermal history of the Earth is, and a lot of the early heat inside the Earth came from accretion, when the solar system was kind of cleaning itself up by planets accreting from dust and larger objects, and everything's sort of clumping together. That releases energy, and that energy is heat, and so that's where some of the initial heat of the Earth is from. It's called the heat of accretion. But then, too, we also have radioactivity, and that was one of the big discoveries early in the last century, was that you couldn't think of the Earth as just being a molten ball that's just done nothing but cool since it was formed, because radioactive elements like uranium and thorium and potassium have actually been creating heat over time.
What would you speculate is going to occur with the increasing fluctuation of magnetic fields?
I don't know what to expect. I really don't. I'm going to say it could reverse polarity within the next century. It certainly could happen.
And if that is the case, George, we are in for the next decades of the remainder of the 21st century for ups and downs in the magnetic field, with people trying to figure out what are the implications. And Jean-Pierre Vallée at the Institute of Earth Physics in Paris, he is concerned that up and down weakening of magnetic fields would be letting in more solar and cosmic ray radiation. It would get maybe further to the Earth, and that he has some concern. He wrote a paper about it, that it could cause destruction of ozone again, that we would have more ozone holes after the ozone has been pretty much repaired. And this also ties into this fascinating paper that Professor Vallée wrote concerning 40,000 years ago, that possibly when there was one of these fluctuations, it was as if the Earth 40,000 years ago was going into a pole flip. There was a change, and it lasted not for very long, but he thinks it was long enough that would have allowed enough UV, ultraviolet light, to get to the surface of the Earth that it could have killed off the Neanderthals that were not prepared biologically for a big increase in UV light getting to the surface of the Earth, because the magnetic field weakened for a period of time. That is his hypothesis. Other scientists have argued that they don't think that there is evidence of species extinctions in the past that ties directly to where they have seen pole reversals. But it is certainly an interesting hypothesis. He is a highly respected physicist, and it is interesting to contemplate that we don't know precisely, no scientist does, what will the impact be if the magnetic field drops even lower. It's been weakening 10 times faster recently, the 6-month measurement just in 2014. I hope people are understanding this is a 6-month measurement in 2014 in which the weakening of the Earth's magnetic field was 10 times faster than normal just this year. So what will happen in 2015, 2016, and beyond? And there is sincere worry that when you look at, let's say, Earth life like bees and salmon and turtles, whales and bacteria and pigeons, they are all dependent upon the geomagnetic fields for navigation.
They sure are. And we're going to continue with this story because what does it do to radiation as well? We'll be back. And welcome back to Coast. Linda Moulton Howe with us with her report, of course, about the Earth's magnetic field. It keeps changing, and I guess, Linda, it keeps changing to a point where it's going to change us, too, isn't it?
Well, I'll tell you, George, if Earth's magnetic poles are getting ready to flip by the end of this century, let's say, then another recent discovery could be a great blessing at this particular time. And it was in the November 27th, 2014 issue of the science journal Nature that NASA announced a surprising discovery hidden inside the two Van Allen radiation belts. The huge irony is that the Van Allen belts that range from about 600 to 25,000 miles above the Earth and were discovered in 1958 by physicist James Van Allen, they are full of high-energy particles of solar radiation and cosmic rays. And they are called the killer electrons in the Van Allen belts. They travel faster than 100,000 miles per second, and they would seriously damage satellites or humans if they were inside of those Van Allen belts. And yet, at 7,200 miles up, scientists have found what they're calling an invisible, impenetrable barrier that is keeping the killer electrons from getting to the Earth's surface. And so far, no one understands exactly how the invisible brick wall protecting Earth got there. In fact, this recent discovery of the invisible shield caught scientists by surprise. Daniel Baker, who is director of the University of Colorado Boulder's Laboratory for Atmospheric and Space Physics, told reporters, quote, "The presence of such a clear, persistent, and seemingly impenetrable barrier to inward transport of ultra-relativistic electrons," those are those ones going at 100,000 miles per second, at this very specific location, and he means a very, very sharp little band inside of the Van Allen belts, presents a substantial puzzle, close quote. Well, one of the Nature paper's authors is Philip J. Erickson. He's Ph.D., originally from Cornell University in space plasma physics, and now is principal research scientist in the Atmospheric Sciences Group at the Massachusetts Institute of Technology's Haystack Observatory in Westford, Massachusetts. I asked Professor Erickson if we've known about the Van Allen radiation belt since 1958, why wasn't the surprising invisible shield to the killer electrons discovered before now? And here is Professor Erickson from MIT's Haystack Observatory.
The thing that's new about, I think, the recent research that we've done is that a couple of years ago, in 2012, NASA launched a twin set of satellites named the Van Allen probes after Professor Van Allen. The detectors on these two satellites, which orbit in and out of the radiation belts, can measure the properties of these electrons with a great deal of precision, much more than we had before. Since these particles are so high energy, even though there aren't that many of them, each one of them, when they pass through something, if they can dump a lot of energy into that thing and, in fact, disrupt it. And so if you are a satellite builder, this is a problem because if you put in a piece of electronics up in space, as these electrons would go through your electronics, the electronics would start becoming overly charged and in some cases would stop working permanently.
And these killer electrons, the source is solar radiation, right?
Right. Ultimately, the idea is that these particular particles are accelerated from lower energy particles by the effects of solar storms and other sort of large energy outbursts from the sun.
Well, isn't that one of the reasons why your discovery is so significant and actually a surprise, that there would be some sort of what is being described as an invisible shield that is protecting Earth from these killer electrons?
Right. Even during times when the sun puts a lot of energy toward the Earth and really pushes on our magnetic field and compresses the charged part of our upper atmosphere, one would expect that the inner edge of the outer belt would move inward as the charged atmosphere shrunk. However, there seems to be a point beyond which these particles do not go. So even though you've shrunk the other parts of the atmosphere, the belts do not follow. They run into some kind of a barrier that we were not expecting. That barrier is remarkably stable. The mission's been operating for 2 years, and it seems to be over there as long as we've looked.
Where would this barrier come from?
Well, there were a couple of speculations, one of which is that if there's a barrier, one has to ask what's happening to the particles if they try to get beyond this point. One of the only ways that one can destroy these particles if they're there is by having them bounce into the atmosphere. At the altitudes that they're at, there is very little atmosphere, so these particles are free to gyrate around the magnetic field and go back and forth in space. However, at some point, if you change their trajectory and knock them a little closer to our magnetic field, they can dip lower and lower towards our atmosphere before they bounce back up and go to the other side of the planet. And when they hit the upper atmosphere, they can get scattered like two billiard balls colliding. So we thought, well, there must be some process that is dumping these particles out if they try to get any closer than this particular 7,200-mile boundary that I mentioned. One of the things that can do that is there are natural waves that are embedded in the space surrounding Earth somewhere in these neighborhoods of a few thousand miles out. These waves are naturally created, just like if you look at waves on a shore, there's various wavelengths that you can see if you stand on the shore and you watch waves rolling in. Well, the wavelengths and the characteristics of those waves are set by the properties of the charged atmosphere that's out in space. So there's a little bit of atmosphere there. That just naturally generates waves. These waves, when they encounter some of these high-energy particles, can alter their travel just a little bit, very, very slowly knock them into the atmosphere. So what we think is happening is these waves called plasmaspheric hiss. If you were to tune a radio receiver to these, they would sound sort of like radio when you tune between stations. There's sort of just a white noise hissing sound. Those particular waves are quite effective at scattering out these particles. The reason that we think that the barrier is there and is very, very stable over months and maybe even longer is that there is a stable population of these waves just inside the barrier. So if the electrons try to get closer than that, the waves start to interact with them and knock them off their travels and end up knocking them to the atmosphere where they get lost. There are some details to be filled in, but that's the current conjecture about why this barrier should be there.
Is it fair to say that Earth life is extraordinarily lucky that this barrier is there?
Sure. The fact that we don't have these very high-energy particles raining into the atmosphere and ionizing life on the ground here has a lot to do with not only the fact that we have an atmosphere over our heads to scatter these, not only the fact that we have a magnetic field that surrounds the planet that can deflect these particles, but that also, as we've shown in this research, that there are extra processes like these waves that also help to insulate us from what is a very nasty radiation environment that is occurring in the space between planets. So yes, we are quite fortunate that we have this. If I were to go to another planet, for example, Mars, which has a very weak magnetic field and a very complicated one, there some of these particles can reach very close to the surface. And so life would be quite different if our magnetic field was weak and quite variable as it is in some other planets.
What would happen to Earth life if this invisible shield were not there?
For the fact that we have an increasingly technological society now, which is depending on objects in space, for example, satellites that sit at geosynchronous altitude and provide things like satellite television, this barrier is, in fact, a considerable help because it means that there are altitudes below which one doesn't really have to worry about these particles being there, and that's a considerable help for people who are designing these sorts of satellite systems. So it's helping life on the ground not have to worry about large radiation doses.
Am I wrong in thinking that the Van Allen belts are dangerous to astronauts and technology if we were in them?
No, you're not wrong. If you were to park yourself at an altitude, say maybe 7, 8, 9,000 miles, and you were to orbit along with these particles for a while, your tissue would suffer radiation damage, much like the way that one gets an X-ray when goes to the doctor's office. You want to limit the amount of X-rays that one gets in a year because that particular hard, highly energetic radiation will ionize pieces of your tissue.
It's odd that it seems to be a combination of something both positive and negative existing in the same belts above us.
That's the way nature often works, is that when you shove on something, it shoves back.
Right. What is the future in terms of studying the invisible barrier further?
The satellites are, in fact, still operating, still taking data, and we hope to continue this mission for another 3 or 4 years. Although we have noticed that this barrier is there, all we can say is that for the 2 years we have been observing, we have never seen things move anywhere closer than this particular barrier. However, we have not seen everything the sun can throw at us. It is likely, in fact, that in the next 3 or 4 years, the sun is entering a descending phase of this solar cycle. In other words, where the sun has peaked in the last 12 months and it's beginning to go a little more quiet. The sun's weather gets more variable. So one can have very large outbursts of energy from the sun that are a little more likely to happen during this next 3 or 4 years. What we're hoping is that if the sun has some very large amount of energy, larger than we've seen to date in this mission, will these boundaries still hold? Or will we have the exceptional case where something actually does move inside this barrier, and if it gets inside there, how long will it last?
What is your perspective on whether or not there is any hard, substantial evidence supporting a Maunder minimum next?
It's very, very difficult to make these predictions.
Mm-hmm.
Space weather is just something that, it's difficult to predict the next 24 hours, let alone the next 10 days, and let alone beyond that.
From my education, when we get to the next solar minimum, which would be in another 5 or 6 years, I believe, in the 11-year cycle, how long would it be before it would be firm that there were no sunspots or so few that it might fall into the category of a Maunder minimum?
Sure. The simple answer is if the solar cycle is an 11-year cycle, if one goes a good fraction of a cycle, for example, 8 to 10 years, and one has not seen another solar peak, you're going to begin to suspect that maybe the sun has in fact shifted to another mode of operation and in fact is now going to be a lot more quiet than it was. I would say it would take a few years of continuous decrease in solar output before people will begin to say, maybe something's changed.
It's another irony that if we did go into a Maunder minimum and the solar output of photons from the sun reduced the warmth on the planet by, say, 0.5% or something,
mm-hmm.
It would be coming at a time where the CO2 and methane buildup is warming the planet,
sure.
And that you would end up with a man-made problem that would be offset by a change in the sun.
That could happen. That's certainly the case. And that would be quite interesting.
Yeah. Wouldn't that be something if the 21st century became dominated by a sun that moved into a Maunder minimum?
Sure. That would have quite the number of implications, certainly for just the incoming solar radiation and for technology disruptions, which would become fewer. Yes, and it might also be a little more difficult to do the studies that I'm talking about. That we are looking at with as many different pieces of data as we can get our hands on, things from the ground, things from low Earth orbiting satellites, things from the Van Allen satellites, things from satellites that are orbiting the moon at the moment, and that's kind of what I get especially excited about.
So, George, the sun might go spotless and cool the Earth down a little bit. Mm-hmm. The magnetic poles might flip by the end of this century, and that would let more solar radiation reach Earth, perhaps off and on, as the magnetic field weakened. And scientists in the military are trying to figure out what to do about cosmic rays and solar radiation. And earlier this year, in February 2014, Discovery News had this startling headline, quote, "Can we hack space to reduce spacecraft damage?" And what is going on? One radiation clearing strategy involves using very large radio transmitters on the ground on Earth to beam very low frequency waves upward, and that these can, in principle, interact with and scatter charges in the radiation belts, and then drive them into the upper atmosphere. It would sort of be like using the radio transmissions to clear out some of the highly energetic particles. And the problem with this approach is getting very low-frequency waves through the ionosphere that we've talked about a great deal on Coast when I have been trying to investigate whether all the booms and the metallic sounds might have something to do with changes in the Earth's core, sending out infrasound up to the ionosphere and bouncing back and making these strange sounds, which may or may not be a part of all of this changing Earth. And there is a scientist, Jacob Bortnick. He's at the University of California in Los Angeles, and he said, contemplating the idea that we might try very low frequency penetrating the ionosphere to clear out some of this radiation that can damage our satellites and could damage any astronauts that we had up there. He said, quote, "It is really mind-boggling to think that there could be human control over such huge volumes of space. On Earth, we control nature all the time, like building dams, but the prospect of doing it in space is fascinating, and it seems a bit like science fiction. And yet, when you go to an area that people have heard in such controversy for so long, HAARP, the High Altitude Auroral Research Project, that has been off and on again, funded and not funded and funded and not funded in Alaska, there is a Air Force Research Lab experiment, again, focusing on the ionosphere, in which they're also trying to see if they can design an instrument that would project very low frequency in the magnetosphere and see if they can explore whether natural and man-made very low frequency waves, including projected from HAARP, could reduce satellite damaging space radiation. So we are trying to see if we can terraform up in that area of the Van Allen belts, where ironically there is also that little band that is protecting the Earth currently. It is showing, all of this put together is showing how absolutely complex the system is of the planet, the atmosphere, the radiation belts, the sun, and that we are in a century in which there may be so many changes happening all at the same time that we will be getting bulletins all of the time about new events that are happening on the Earth because of what is happening in space above us.